Welcome back, guys. We're going to go into another lecture today, and today we're going to cover heat, temperature, and density altitude. Now, these are all very important items that will affect you as a pilot, so we really need to pay attention and learn as much as we can about this today. All right, so let's jump into it. All right, let's talk about heat and temperature. Temperature is one of the most basic variables used to describe the state of the atmosphere. Air temperature varies from one season to the next, between day and night, and literally can be between hour to hour. Air temperature also varies from one location to another, from high altitudes and latitudes to low altitudes and latitudes. Temperature can be critical to some flight operations. As a foundation for the study of temperature effects on aviation and weather, this chapter that we're going over today describes temperature measurement and heat transfer and imbalances. Okay? So I'm going to blow this up like I normally do. That way we can look at it all together and everyone can see it really well. So matter. Matter is the substance of which all physical objects are composed. Matter is composed of atoms and molecules, both of which occupy space and have mass. The Earth's gravity acting upon the mass of matter produces weight. Now, energy is the ability to do work. It can exist in many forms and can be converted from one form to another. For example, if a ball is located at the edge of a slide, it contains an amount of potential energy, or energy of position. Now, this potential energy is converted into kinetic energy. That's energy of motion when the ball rolls down the slide. Atoms and molecules produce kinetic energy because they are in constant motion. High speeds of motion indicate higher levels of kinetic energy. Now, when you have high levels of kinetic energy, you have heat. Now, heat is the total kinetic energy of the atoms and molecules composing of a substance. The atoms and molecules in a substance do not all move at the same velocity. Thus, there are actually a range of kinetic energy among the atoms and molecules. Now, temperature is a numerical value representing the average kinetic energy of the atoms and molecules within matter. Temperature depends directly on the energy of molecular motion. Higher temperature, or warmer, indicates higher average kinetic energy of the molecular motion due to faster molecular speeds. Lower temperatures indicate a lower average kinetic energy of molecular motion due to slower molecular speeds. Temperature is an indicator of the internal energy of the air. Okay? So temperature measurements. Now, we use thermometers as an instrument that we use to measure temperature. Higher temperatures correspond to higher molecular energies, while lower temperatures correspond to lower molecular energies. Now, temperature scales. Now, we have talked about this Kelvin scale briefly, but let's look at it. So many scientists use the Kelvin scale, which is a thermodynamic or absolute temperature scale, where absolute zero is where the theoretical absence of all thermal energy, or that's 0 Kelvin. Now, if you refer back to the previous lectures, you know that absolute zero is the point at which all molecular motion ceases. So at absolute zero, there's no molecular motion, right? All right. So, because nothing can be colder than absolute zero, the Kelvin scale contains no negative numbers. So, the Celsius scale is the most commonly used temperature scale worldwide and in meteorology. The scale is is approximately based on the freezing point of 0 degrees Celsius and the boiling point of 100 degrees Celsius of water under a pressure of 1 standard atmosphere, or approximately sea level. Each degree on the Celsius scale is exactly the same size as a degree on the Kelvin scale. Now, in the early 1990s, the United States aligned with ICAO standards by moving to the metric system for aviation weather reports. While some websites and applications provide temperature from the METAR in degrees Fahrenheit, these are done by conversion software, as the temperature in the METAR is strictly reported in degrees Celsius. The United States uses the Fahrenheit scale for everyday temperature measurements and for non-aviation purposes. In this scale, the freezing point of water is 32 degrees Fahrenheit and the boiling point is 212 degrees Fahrenheit. So what is heat transfer? Heat transfer is energy transfer as a consequence of temperature difference. When a physical body, another object or fluid, is at a different temperature than its surroundings or another body, transfer of thermal energy, also known as heat transfer or heat exchange, occurs in such a way that the body and the surrounding areas reach thermal equilibrium, or a balance. They reach the same temperature. Heat transfer always occurs from a hotter surface or hotter object to a colder surface or colder object. Where there is temperature differences between the objects in proximity, heat transfer between them can never be stopped. It can only be slowed down. It will continue, but it will not. It will continue. It can be slowed, but it will not stop. The heat source for the surface of the earth is the sun. Energy from the sun is transferred through space and through the earth's atmosphere to the earth's surface. The sun is the primary source of Earth's weather. Let me repeat that because you need to know this and remember it. The sun is the primary source of Earth's weather. You will be asked on a quiz, an exam, or by me just in everyday dealings out at the airport, hey, what's the source of all weather on Earth? Hey, Shannon, that's the sun. So you need to be able to tell me that, okay? There are 3 different ways. Let me go back up. Since the energy warms the surface and the atmosphere, some of it becomes heat energy. Now, there are 3 different ways that heat is transferred into and throughout the atmosphere, and those are radiation, conduction, or convection, or a combination of the 3. Heat transfer associated with heat exchange of water from one phase to another. Liquid water absorbs heat, changes to vapor and liquid. Water releases heat when it is changed to ice. Now, this can be fundamentally treated as a variation of convective heat transfer. The heat transfer associated with water will be discussed in Chapter 6. Water vapor, again, I'm taking this from the FAA. So just don't pay attention to that last part of that. We're going to talk about it here. All right, so radiation. If a person has ever stood in front of a fireplace or near a campfire, then they have felt heat transfer known as radiation. The side of the body that is nearest the fire warms, while the other side remains unaffected by the heat. Although people are surrounded by air, the air has nothing to do with this type of heat transfer. Heat lamps that keep food warm work in the very same way. I just think I had 2 of the same slides there. Now, radiation is the transfer of heat energy through space by electromagnetic radiation. These electromagnetic waves travel at the speed of light and are usually described in terms of wavelength or frequency. Frequencies range from gamma rays on the high end to radio waves on the low end. Also contained in the spectrum are X-ray, ultraviolet, visible, infrared, and microwaves. All objects emit or radiate energy as the heat energy within the object is converted to radiation energy. This transmitted radiation passes through the entities such as air, water, or space. Along the way, the radiation can be reflected, which occurs when the wave energy changes direction when encountering an object. Eventually, the radiation is absorbed and the electromagnetic wave energy is converted to heat energy by the absorbing object. The emitting object loses heat energy and the absorbing object gains heat energy during this process. Heat transfer. So solar and terrestrial radiation. All objects emit radiation energy, including the sun, solar radiation, and the earth, terrestrial radiation. An object's wavelength of maximum radiation is inversely related to the temperature. The hotter, colder the object, the shorter or longer the wavelength. The sun's wavelength of maximum radiation is relatively short and centered in the visible spectrum. The Earth's wavelength of maximum radiation is relatively long and is centered in the infrared spectrum. So if you look to the right there, you'll see the sun. The hotter object emits shorter wavelengths while the cooler object emits longer wavelengths. All right? The Earth is definitely cooler than the sun, therefore our wavelengths are longer than the sun's. So some of the solar radiation that reaches the Earth's surface is radiated back into the atmosphere and becomes heat energy. Dark-colored objects such as asphalt absorb more of the radiant energy and warm faster than the light-colored objects. Dark objects also radiate their energy faster than light-colored objects. Let's talk about conduction. Now, conduction is the transfer of energy, including heat, by molecular activity from one substance to another in contact with it through that substance. Heat always flows from the warmer to the colder substance. The rate of heat transfer is greater with larger temperature differences and depends directly upon the ability of the substance to conduct heat. During conduction, the warmer substance cools and loses heat energy, while the cooler substance warms and gains heat energy. Heat, thermal conductivity, is a property of the substance that indicates its stability to conduct heat as a consequence of molecular motion. Units are watts per meter Kelvin, WM1K1. Now I want to bring up the board here just for a second, and I want to kind of sort of explain conduction, because that is a very convoluted way and scientific way of telling you a very simple thing. So let's pretend we've got a pot, and our pot is on the stove, and we got water in the pot. Okay? Well, while we have water in the pot, we also have a metal spoon that's down here in the pot. The spoon is cold. Well, if we turn the heat up, the fire up, and we get this water to boiling, what's going to happen to the spoon? The spoon is going to get hot. This is conduction. Very simple. The heat energy that is in the boiling water goes into the spoon, which is the cooler substance. Therefore, the spoon gets hotter. Conduction. Okay? Very simple. Don't get worked up over it. It's not that big of a deal. Okay? Let's talk about convection. Convection is the transfer of heat within a fluid, such as air or water, via motions of the fluid itself. This type of heat flow takes place in liquids and gases because they can move freely and it is possible to set up currents within them. Water boiling in a pot is an example of convection. Now, I just used a pot on a stove and boiling water. Now, the process of the spoon getting hot is conduction, heat transfer from one to another. The actual process of the water boiling in that pot is convection. You're taking water, heating it from below. As the water molecules inside the water start bouncing around and moving faster and faster and faster, it sets up currents inside that water, and finally it starts to boil and boil and boil. Okay, so that is convection. Because the air is a poor thermal conductor, convection plays a vital role in the Earth's atmosphere heat transfer process. So what is that thermal response that we're going to see? Whether by radiation, conduction, or convection, or a combination of these things, the temperature response to the input or output of some specified quantity of heat varies from one substance to another. Specific heat capacity, also known as specific heat, is defined as the measure of heat energy required to increase the temperature of a unit quantity of substance by a certain temperature interval. Now that is a very long and convoluted way to say it's the amount of heat you have to put in something to get the temperature to change, okay? So just be able to know that, and be able to answer quiz questions, test questions on it. That's all it is. It's just the amount of heat needed to change the temperature, okay? So specific heat capacity is typically expressed in units of joules per gram Kelvin, JG1K1. Thus, two different substances with identical temperature measurements do not necessarily possess the same amount of heat energy. When exposed to the same amount of heat energy, a substance with a low specific heat capacity warms up more than a substance with a higher specific heat capacity. So temperature variations with altitude. Now this is very important, okay, because this first sentence in this slide here talks about a lapse rate. Now lapse rate is very important in thunderstorm production, okay? So a lapse rate is lapse rate of temperature is defined as a decrease in temperature with height. That's all it is, okay? It was stated that the temperature decreases 6.5 degrees Celsius or 3.5 degrees Fahrenheit per 1,000 feet in the standard atmosphere. But since this is an average, the exact value seldom exists. In fact, temperature in the troposphere sometimes remains constant or even increases with height. So if we remember back to when I lectured on the different layers of the atmosphere, if you remember when we talked about the troposphere, you know, I drew on the board how it decreased with height, and now in the troposphere, after we break through the tropopause, temperature actually increases with height. That's what this is talking about. Caution should be taken when using the standard lapse rate to estimate the freezing level. Quite often the boundary layer is dry adiabatic, and the estimate of the freezing level could be an error. Now, I don't want you to get too bent out of shape about the dry and wet adiabatic lapse rate. I used to teach that a lot. I'm not going to be too much concerned with that with you guys, because that really gets into some advanced meteorological theory, and I don't want to confuse you. So just know that the boundary layer is dry adiabatic, and therefore estimating the freezing level, you could make a mistake and wind up in trouble. Okay. So what is an atmospheric sounding? You've heard me mention this before. An atmospheric sounding is a basic. Let me come back to you just for a second. Now, this is what the FAA and the scientific world says an atmospheric sounding is. I want you to know this. An atmospheric sounding is nothing more than the National Weather Service sending up a balloon, and as it goes up through the atmosphere, it takes temperature, pressure recordings, and things of that nature and gives them data to let them know what the atmosphere is doing, okay? That is all an atmospheric sounding is. So let's look at what the FAA says. The atmospheric sounding, or simple sounding, is a plot of the vertical profile of one or more atmospheric parameters such as temperature, dew point, or wind above a fixed location. Soundings are used extensively by weathermen, I'm getting tongue-tied this morning, to determine the state of the atmosphere. Okay? Now, it's important for us to understand what the atmosphere is doing at different levels, because what the atmosphere is doing at different levels, it makes weather. Weather greatly impacts and affects your job performance as a pilot. So these atmospheric soundings are very important. Now, am I going to have you to understand and know exactly what they're looking at when they go send the balloon up? No, because I get confused on that. And I'm not going to make you learn that. Just know that a sounding is just different pressure, temperature recordings from a weather balloon, and it helps them to determine what our weather is going to be, okay? Now this right here, this temperature inversion, you need to pay attention to. Temperature inversion is very important in aviation. It could bring some nasty stuff with it, okay? So let's look at it. A temperature inversion, or simple inversion, is a layer in which the temperature increases with altitude. Well, Shannon, why is that important? Well, down here, in the troposphere where we're at right now, what does the temperature normally do when you increase in altitude? Well, normally, as you go up in altitude in the troposphere, the temperature decreases. So this inversion flops that around. The higher you go, the warmer it gets. And that could make for some nasty weather, okay? If the base of the inversion is at the surface, it is termed a surface-based inversion. I said invasion, I meant inversion. If the base of the inversion is not at the surface, it is termed an inversion aloft. A surface-based inversion typically develops over land on clear nights when the wind is light. Now, I want you to think about, here in Arkansas, especially up here around Melbourne. We have hills, we have valleys, right? Well, in the morning times, especially during the spring, fall, somewhere in there, you take off early and you go to flight, you see fog laying in those low valley areas. That is this temperature inversion. So if you have a surface-based inversion, know that you are probably going to deal with fog, all right? The ground radiates and cools much faster than the air above it. Air in contact with the ground becomes cool when the temperature is a few hundred, let me start again. Air in contact with the ground becomes cool while the temperature a few hundred feet above the ground changes very little. Thus, temperatures increase with height. An inversion may also occur at any altitude when conditions are favorable. For example, a current of warm air aloft overrunning cold air near the surface produces an inversion aloft. Inversions are common in the stratosphere. Now, that goes back to what we had talked about earlier. When you break through the tropopause and get into the stratosphere, temperature increases with height. That's what this is talking about, okay? The principal characteristics of an inversion layer is its marked stability. So very little turbulence can occur within it. Now, that's a good thing for us, right? So if you get into a layer up in the air and you've got really smooth air, you're probably in an inversion. Well, what's that marked by? Could be haze. If you'll notice, I'm sorry about that, if you'll notice, if you've ever been up and it's been real hazy, there's probably a little bit of an inversion going there. So if you see a haze layer and you're flying in that haze layer, you're going to have smooth air because that is a marked inversion layer, okay? This is very, very, very important. You will need to know what density altitude is from now until the day you stop flying. I promise you, you will be asked on a quiz, an exam, and check rides, what is density altitude and how does it affect your aircraft? So you must pay attention to this, or you're going to make things very, very difficult for yourself if you don't. Okay? So let's look at it. Density altitude is pressure altitude corrected for non-standard temperature. When you're asked what is density altitude, that is what we want you to say right there. Density altitude is pressure altitude corrected for non-standard temperature. Okay? Now, density altitude decreases aircraft performance. So if you got high density altitude, your airplane's not going to fly as well as it does on a low density altitude day, okay? Density altitude bears the same relation to pressure altitude as true altitude does to indicated altitude. Here is the quiz you're going to need for the quiz this week. It's capital B, E-A-C-H, capital B, A-L-L-S. Now, I want to make sure I'm at the right spot. Yeah, I am. So, Shannon, why beach balls for the password? You're fixing to understand why, okay? So when we start talking about high and low density altitude, as you've heard me say previously, I think visualization helps you learn better, okay? So here we have a parcel of air that has high density altitude, okay? And here we have a parcel of air that has low density altitude. So what is the difference, Shannon? Well, when you think of high density altitude, I want you to think of beach balls in this parcel of air. All right. Now these beach balls are high temps, high humidity, okay, in every single one of these. Well, when all of this increases, this is the actual air that you have to work with. So in high density altitude, is the prop of your airplane going to be able to grab a hold of this actual air? Or is it going to grab a hold of all of this? It's going to grab a hold of the high temperature, high humidity, moisture, and all that that's in the air, right? You've got all of this stuff making the air spread out. So the prop is not going to grab a hold of the air, so you have lower performance. Okay? Well, now let's look at low density altitude. So if high density altitude is beach balls, I want you to think of low density altitude as ping pong balls. All right? So now all of these are the moisture and the temperature and everything that are right here. Now your air is all here. So on a low density altitude day, is your propeller going to grab more of the air or more of the bad stuff that we don't want? It's going to grab more of the air. Therefore, you have a higher, and I guess I should have did this, aircraft. You have a higher aircraft performance. Okay? So know that the higher the density altitude, the lower your aircraft performance. The lower your density altitude, the higher your aircraft performance. That is why the password for this week is beach balls. All right? So higher density altitude, think of it as beach balls. All right? And these beach balls are full of just high temperature, high humidity, and it forces the air out. If all that temperature and humidity is there, there's less molecules of air for your propeller to grab a hold of and your airplane to perform on. Where it's low density altitude, there's more particles of air for that propeller and that airplane to use. Okay? So if it's low, you have higher performance. If it's high density altitude, you have lower aircraft performance. All right? So I want you guys to remember that, because that is vital to your everyday flying that you're going to do, and you will need to understand this from now until you stop flying. However many years from now that is, you need to understand what high and low density altitude is. Okay? Now, density altitude is indirectly related to the atmosphere density. As air density increases, the density altitude decreases. So that is those ping pong balls I was talking about. That's the density of the air. So as the density of the air increases, so as I put air up there, as that increases, the density altitude decreases. Okay. Well, as I'll show you here, and conversely, as air density decreases, density altitude increases. So as all of that heat and humidity and all that increases, it spreads out those air molecules. Higher density altitude, lower aircraft performance. Well, as the air molecules and all that heat and temperature and all of that goes away, and those air molecules come back in and get real big again, and all that other stuff gets real small, you have a low density altitude, higher aircraft performance. All right, density altitude equals field elevation during standard atmospheric conditions, but conditions are rarely standard. Density altitude is higher or lower than standard at airports that report lower or higher than standard pressures. Standard pressure is 2.9 or 0.9 or 2. So if anything's higher or lower than that, that's when density altitude comes into play, right? Temperature is the most important factor since temperature has the greatest effect on density horizontally in the atmosphere. Remember that, remember that, remember that. Temperature has the greatest effect on density altitude. On hot days, the air becomes less dense, causing high density altitudes. On cold days, the air is denser, causing lower density altitudes. Think of it like this. Your body, if it's, let's say you play sports. What do you do before you go play sports? You warm up, right? So as you warm up, your muscles become loose. It's the same thing that happens to the atmosphere. As the temperature increases, the atmosphere spreads out or becomes loose, becomes more pliable, right? Those air molecules that your airplane needs to perform spread out. Now let's think about your body again. You're an athlete, but it's cold. You don't warm up. Your muscles are tenser. You don't get as much, you're tensed up. Same thing with the temperature. The atmosphere actually condenses down and becomes tighter when it's colder. When that condenses down, it condenses all those air molecules down and they become more for your airplane to use. So the hotter, the higher the density altitude, the colder, the lower the density altitude. The hotter, the less your aircraft will perform, the colder, the better your aircraft will perform. All right, so dew point or water vapor is also a contributing factor, but its effects are generally negligible, okay? Density altitude is an index to aircraft performance. Higher density altitude decreases aircraft performance. Lower density altitude increases aircraft performance. High density altitude is a hazard since it reduces aircraft performance in the following ways. Number one, it reduces power because the engine takes in less air to support combustion. Number two, it reduces thrust because there is less air for the propeller to work with, or a jet has less mass of gases to force out of the exhaust. Number three, it reduces lift because the light air exerts less force on the airfoils. A pilot cannot detect the effect of high density altitude on the airspeed indicator. The aircraft lifts off, climbs, cruises, glides, and lands at the prescribed indicated airspeed, but at a specified indicated airspeed, the pilot's true airspeed and ground speed increase proportionally as density altitude becomes higher. So just looking at your airspeed indicator, you cannot indicate how the density altitude is affecting your aircraft. Just know that it is. The net results are that high density altitude lengthens a pilot's takeoff and landing roll and reduces your rate of climb. It's going to take you longer to get off the ground and you're going to get away from the ground a lot slower. Before liftoff, the plane must attain a faster ground speed to generate the same amount of lift needed to get off on a lower density altitude day. The plane lands at a faster ground speed and therefore needs more room to stop. At a prescribed indicated airspeed, it's flying at a faster true airspeed and therefore covers more distance in a given time, which means climbing at a shallower angle. Adding to this are the problems of reduced power and rate of climb. Figure 8.15 shows the effect of density altitude on takeoff distance and climb rate. So let's look at this. So the top depiction shows that density altitude is at sea level. Your takeoff roll is 1,300 feet and you'll climb out roughly about 1,100, 1,200 feet per minute. Now let's look at what happens if we put that density altitude at 5,000 feet. It's going to take you approximately 2,000 feet, 1,800, to get off the ground. But you're only going to climb at 600 to 700 feet per minute. Now, if those mountains were there, you're going to hit the side of that mountain. So it's very important that you understand how density altitude affects your aircraft. High density altitude can also be a problem at cruising altitude. When air temperature is higher or warmer than the standard atmosphere, the higher density altitude lowers the service ceiling. It lowers how high your airplane can fly. For example, if the temperature at pressure altitude of 10,000 feet is 20 degrees Celsius, density altitude is actually 12,700 feet. A pilot's aircraft will perform as though it is at 12,700 feet. See how that could be a problem? So to compute density altitude, a pilot can set the altimeter to 292, read the pressure altitude from the altimeter, obtain the outside air temperature, and then use a flight computer to compute density altitude. Guys, I can't stress this enough, okay? Density altitude is a very big deal. There have been pilots that have lost their lives because they tried to make their airplane perform in such high density altitude situations and it just couldn't. So let's take this and learn it and apply it, okay? Because I do not ever, ever, ever want to have to look at any of your family and tell them, well, they're hurt because they didn't listen. All right? Well, that's going to be it for density altitude, temperature and pressure. So, as always, your work is due by 11:59 p.m. on Saturday night. Make sure to do your discussion post. I look forward to reading your discussion posts. As always, you guys put up some good ones. I'm proud of you guys. So until next time, have a good week. Happy flying and blue skies. See you later, guys.